this up. Okay, so today we're going to finish 310. I really just want to talk about the stuff that we need for test 3 and the final. And then there's other stuff in there that you can go through on your own time. But like I said, I'm only going to cover what we need from 310 because then I want to spend the rest of the time reviewing for test 3. So, and this is the last section in chapter 3. And we're on to chapter 4, and that's our last chapter. So, section 310 is on linear approximation and differentials. So the problems that we're going to have to do are going to be on linear approximation. I'll just introduce differentials, mostly because once you go into Calc 2, we'll use those a lot. And so they'll kind of reintroduce them quickly, but it'd be nice if you've seen them once before. Okay, so linear approximation is, okay, so if we've got a function, let's make it some wonky curve, right? Then we know that the tangent line, right? The slope of the tangent line, we can move it closely. If we zoom in on some point, then the slope of the tangent line is essentially the same as the slope of the curve, right? And so if we want to figure out, no worries. If we want to figure out what this curve looks like at some point, right, and maybe evaluate this curve, then we can use linear approximation. So we have seen that a curve lies very close to its tangent line. So we've seen that a curve lies very close to its tangent line. Near the point of tangency. Near the point of tangency. So if we're given a function, so given a function y equals f of x, we can approximate the function y, right, at some point. We can approximate the whoops, don't know what happened there, but okay. We can approximate the function by its tangent line over small intervals. We can approximate the function by the tangent line over small intervals. So what we mean is, okay, we've got a graph here, and I've got some curve that might look like this, something like that. At some point, let's call it A. Can trace up. And at this point, the function, right, is going to be at f of a. Y equals f of a. Guess I'm a little bit wonky, but that's okay. If I put a tangent line on here, right, at x equals a, then I know my tangent line is going to just touch that point Maybe something like that. And I can say that this line y equals L of x, so capital L of x, where L of x is the linear approximation. And of course, this dark one is y equals f of x. There's going to be kind of a range around A where this linear approximation is going to be good, right? And so that's why we say that we can approximate this function. If we can find the slope or the equation of the tangent line, then I can use that to evaluate the actual function y equals f of x for points close to A, right? And so we're going to have some sort of kind of buffer here. Right. Looks like for A between maybe these values, right, this linear approximation would do a decent job of approximating the curve. Right. And so here, I'll just say that this, we'll just say is a small interval around A. So we're not going to define what this small interval is, right? We're going to move just a little bit off of A, and we'll still be able to approximate what this function is at those points. So what we need to do, right, to find this linear approximation, then we need to find the equation of a tangent line, which we've done a lot of times earlier in the course, right? We found equation of tangent lines. And so here's one of the uses for it. I know for me, it's kind of hard to convince myself that I need to do this, right? Because what you'll see in the examples is we could just use our calculator and be done with it, right? But let's say you don't have a calculator, right? And then we need to be able to approximate these things. And so this is one of the tools. So of course, thinking pre-calculator times, right? This would have made your life so much easier if you had to evaluate these functions. So, and we cover it because we have to find the equation of a tangent line, and then we can use it. And then we also introduce this idea of linear approximation. So, I'll just start with, we know how to find the equation of a tangent line. So we know how to find the equation of a tangent line. Right? We've done it a few times, or I want to say more than 5 times at this point. So, and you've probably done it in the lab as well, right? Using Maple. But the first thing that you have to do, right, is find the slope at x equals A. The slope, well, that's going to involve find the derivative. Right. This is going to be f prime evaluated at A. That's the slope at x equals A. Just by the definition of the derivative. And then second, right, we need to have a point. But if I've told you, okay, we need to evaluate this thing at x equals 2, well, then you know what 2 is, right? And you'll be able to find, or 2.01 or something, right, a little bit off. So we find the slope of the tangent line at 2, we find the f of 2, and then we've got x equals 2, so we've got this point, and so use the point a f of a in the point slope form of a line, right? Because now I've got a slope, I've got a point in the point slope form of a line, which says that y minus y naught is m times x minus x naught, right? Where the point that you know here, a f of a is going to be x naught, y naught. And then m is, of course, the slope. So f prime a equals m. Okay. So if we've got our point, we've got our slope, so now we can construct our point slope form of the line. So we've got y minus, I guess I'll write it out because it's a new page here. Move it up a little bit. Y minus y naught equals m times x minus x naught. In our case, we've got y minus f of a is f prime at a, well, that's the slope, times x minus a. If we just add f of a to both sides just to get it in the form of y equals something, we can have y equals f prime at a times x minus a plus f of a. So this equation here, that's going to be your L of x, right? This is your linear approximation. L of x is the linear approximation at x equals a. Okay. So that's going to be that line, but then what we said is we can move out for small increments, right, around a, and we can still use this linear approximation to evaluate f of x. So we can summarize it in a little blurb here. The linearization of f of x at x equals a is the function L of x equals f prime at a times x minus a plus f of a. So just from before. But I will put a box around it. You can pretty easily develop that, right, on your own, just knowing what the slope is and that the derivative evaluated at a is the slope at a, right, and we can kind of figure it out. So what we say is that, okay, well, f of x is roughly equal to the linearization at x for x values close to x equals a. For x values close to x equals a. And that's the whole idea of what we're going to be doing today, where the only thing that's new is just finding this linearization or the linear approximation and then evaluating for numbers around that value. So let's do an example. Yeah. Oh, go ahead. Oops. So we want to find the linear approximation. Find the linear approximation of f of x equals, we'll start small here, x plus 3 at a equals 1, and use it to approximate the root of 3.98 and the root of 4.05. 4.05 or 4.01? 5. And use it to approximate the numbers the root of 3.98 and the root of 4.05. And then we'll just follow it up with, are these over or underestimates? Hey, look, we've got a cute bird on the window. Oh, you see it? He's sitting on this side of the wall. Oh, he's off. He's gone. Are these approximations over or underestimates? That's going to depend on what our curve looks like, right, at A. So if we've got a curve that looks like this, and we want to know that A is here, then my linear approximation, right, is always going to be slightly above what the actual curve is, right? Versus if my A is here, maybe here, then I'm going to be constantly below the curve with my linearization. So we'll use a calculator to compare the values to the actual values, or to compare the approximation to the actual values. But that's what's going on. So, all right. Or maybe I should put a little note here. Overestimates or underestimates. All right. So first thing we have to do, right, is we have to find the equation of the tangent line at A equals 1. Yeah. So first we find the equation of the tangent line. The equation of the tangent line at x equals 1. So that means that I'm first going to have to find the derivative of the root of x plus 3. And so if f of x is the root of x plus 3, then f prime of x is going to be, well, I can rewrite this as x plus 3 to the power of 1/2. So then I get 1/2 times x plus 3 to the negative 1/2. Technically times 1, right? Because I have to use the chain rule, right? And so I can rewrite this as 1/2 root x plus 3. Because I've got the power of negative 1/2. The negative puts it in the denominator, but the 1/2 makes it a square root. So f prime at 1 at x equals 1, because that's the point we're interested in, is going to be 1 over 2 root 1 plus 3. So I've got 1 over 2 times 2, which I'm just going to go straight to 1 over 4. So that's the slope of the tangent line. Slope of the tangent line at x equals 1. So now, at x equals 1, we know that a is 1 and f of a, of course, is f of 1. F of 1 is going to be the root of 1 plus 3, puts me at 2. Notice that so far, all of these things that we're calculating, we've been able to do in our heads. Of course, you know, if we didn't have a calculator, we would probably be better at arithmetic. And this, I mean, the stuff that we're about to see is going to be a lot easier too, but that's okay. Okay, so we know the point. Right, so the slope, or I guess the point is going to be at 1, 2, and the slope is going to be 1 over 4. And so you can start with the L of x function that we established earlier here, this one, or you can just develop it, right? That way you don't have to crowd your brain with more stuff, right? We need to know how to find the equation of a tangent line anyways, so we may as well just develop it every time. I don't really see the harm in that. So we've got y minus f of a is f prime at a times x minus a. Just plugging in those numbers. And so we get y minus 2 is 1 over 4 times x minus 1. I get y is 1 over 4x minus 1 over 4 plus 2. 1 over 4x, I'm just going to write as x over 4 from now on. But then to combine negative 1 over 4 plus 2, right, I need a common denominator. And so what I've got is I've got x over 4, and then negative 1 over 4 plus, and then I need to get 2 over 4, so I could rewrite that as 8 over 4. Or just multiply 2 by 4 over 4. You get 2 times 4 is 8 over 4. So I just kind of skipped showing that step. But now I'm going to have x over 4 plus 7 over 4. X over 4 plus 7 over 4. So what's this saying? This is saying that for the curve of the root of x plus 3 at x equals 1, right, we can approximate what y is or what f of x is by using x over 4 plus 7 over 4. So the corresponding, so the linear approximation, skip some words here. So the linear approximation is that the root of x plus 3 is roughly equal to, just to match my notes here, I've got 7 over 4 plus x over 4. Just shifted the order. When x is near 1, when x is near 1, right? That's important because we've seen that this line just keeps going and going and going, right? So at some point it's going to start lifting off and it's no longer a good approximation. So around 1, then we're safe, right? Around x equals 1. So if we want to find the root of 3.98, well, then I know that x must be 0.98. So then we can approximate this by 7 over 4 plus 0.98 divided by 4. So here's what I mean where if we didn't have calculators, our arithmetic would be way better. I don't feel comfortable taking 0.98 divided by 4, right? But of course, that's because I've had a calculator all my life. And so it's not that bad, right? We can divide it and we can figure it out. But what we get is 7 over 4. I will cheat and use my 0.98 divided by 4 is 0.245, and then 7 over 4. So we get 1.75 plus, and then what did I say? 0.98 divided by 4? 0.245. It's only because I've been ruined, and I don't think I'm the only one who's been ruined, right? We should be able to calculate these things, but it's okay because we've got calculators, so that's not the point, but that would be reasonable to calculate. Yeah. So the 0.98, because we're looking at the root of x plus 3, right? If I want the root of 3.98, I'm assuming 3.98 is close enough to 3, right? Sorry, that 0.98 is close enough to 1, right? Because then my x is 0.98, which it should be. Right? So then my x is 0.98, and that's why I'm using the 0.98 there. So then this puts us at plus 1.75. Also, because I don't want to muck it up here, 1.995. This is our linear approximation. And so this is our approximation. And what we can do is the actual, if we do the root of 3.98 on our calculator, well, I shouldn't even use an equal sign, but the root of 3.98, I'll say is still approximately equal to, right? Because as long as I've got decimals that keep going in my calculator, I'm doing an approximation here. And so, but the calculator says it's 1.9949937334. And then I'll say from calculator. If we have to look at this and decide if our approximation was an overestimate or an underestimate, looks like our approximation was slightly over what it should have been, right? 1.995 is slightly over 1.99499, right? And so here, therefore, we have an overestimate. If we do the same thing for the root of 4.05, the root of 4.05, I should clarify that that's the root of 1.05, oops, 1.05 plus 3, almost wrote 4. So my x must be 1.05, right? Which again, I'm going to assume is close enough to 1 to get a reasonable approximation. But we'll see. So this is going to be 7 over 4 plus 1.05 divided by 4, which again is 1.75 plus 1.05 divided by 4 is 0.2625 plus 1.75. Get roughly 2.0125. Which, if we check in kind of logically, if I take the square root of 4, I'm expecting 2, and so here, right, and same thing earlier, right, I was still expecting something around 2, right, because I'm so close to the square root of 4 here. But now we've got 2.0125, and if we do the same thing, and kind of, we'll call it the actual, but because it's an approximation, it's not going to be. The root of 4.05 on our calculator is roughly 2.012461118 from calculator. So again, and it makes sense that we would consistently have an overestimate in this case, right? But again, therefore, we have an overestimate. This is where it might be helpful to know what these different graphs look like, right? So remember at the beginning of the term, we spent time talking about what these graphs look like. And so knowing that the root of x plus 3 looks something like this, y equals the root of x plus 3, and here I'm at -3, then at 1, I see that my line is going to be just kind of over. I wasn't able to touch the curve, but that's okay. Right, here's my linear approximation, which is consistently going to be above the curve, right? And so that's why we've got these overestimates. Nice. Any questions about that one? No. Okay. How about we do another one then? I do find that after we've spent time doing things like implicit differentiation, right, especially implicit differentiation, but also related rates and things like that, this stuff is kind of, what's the catch? Why is it so easy? But this is just it, right? So it should be kind of easy marks. Hopefully, that's what I'm hoping for. And there will be one on test 3, and there will be one on the final, right? So, so that'll be good, right? Because we've done some hard stuff in chapter 3, especially this this later chunk of chapter 3. So now it's kind of, you guys are a little bit, you don't trust me anymore. Why is this so easy? I don't know. This is it. So we might get a curve where we have to use implicit differentiation. It's not likely, right? We've seen the chain rule. We're about to see the chain rule again. But we could. So we have to be prepared. Find the linearization, but it's not likely. Find the linearization of f of x equals, oops, you know what, I'll put it down here. F of x equals 4 times the root of x squared minus 9 at x equals 5. Use it to approximate f of 5.1. Use it to approximate f of 5.1. I'm pretty sure on test 3, it'll be broken up. It'll just be one question like this. On the final, don't be thrown off. I'm pretty sure it's part A, find the linear approximation. Part B, use the linear approximation to evaluate it at this point. Right? And so it just breaks it up and makes it look like a long question, even though it's not. Okay, so we know that we need to find, well, let's just jot down. So our linear approximation is f prime of a times x minus a plus f of a. You can have that memorized, or you can just go ahead and find the equation of the tangent line, right, by finding the slope and finding a and f of a. Really doesn't matter. So we're saying that a is going to be 5 in this case. So on the side here, I can find f of 5, which is 4 times 5, the square root of 5 squared minus 9, which is 4 times the square root of 16, which is just 4 times 4, which is just 16, confusingly. Maybe it's not confusing to you. I never like when the same number reappears as something else. I don't like that. Actually, might need more room here. I need to find the derivative of f prime of x. Well, if f of x is 4 times the root of x squared minus 9, I'm going to rewrite that root as, I'm going to put it down here, 4 times the root of x squared minus 9, which I can rewrite as 4 times x squared minus 9 to the power of 1/2. If I have to take the derivative of this, right, I'm looking at a chain rule here. I've got an outside function and an inside function. And so I've got 4 times 1/2 times x squared minus 9 to the negative 1/2 times the derivative of the inside, which is just going to be 2x. I'm multiplying all along here, and so I can cancel this 2 and this 2. If you don't want to do it right away, that's okay, but they'll end up canceling at some point, so it doesn't matter when you do it. So then I'm looking at 4x in the numerator and then the root of x squared minus 9 in the denominator. So I've got 4x over the root of x squared minus 9. This is the slope of the tangent line at any value of x on this curve, right? But we want the slope of the tangent line at x equals 5. So we want f prime at 5, which is 4 times 5 over the root of 5 squared minus 9, which I'm going to keep as 4 times 5 for a little bit longer, over the square root of 16. Yeah. Over 4. So I'm just left with 5. So A is 5, but also f prime at 5 is 5. Should have picked better numbers. That's okay. So therefore, L of x is going to be f prime at 5 times x minus 5 plus f of 5, which in our case is going to be 5 times x minus 5 plus, and what was f of 5? 16. Plus 16. So I get 5x minus 25 plus 16. I'm just going to go straight to 5x minus 9. Mostly because I've got that page break there. So on the final, that would be your part A, right? Where you're just finding the linear approximation at x equals A, or x equals 5 in this case. So now we can use this to evaluate f, or approximate rather, f of 5.1. So now we're going to use this to approximate f of 5.1. So what we're saying is that f of 5.1 is roughly equal to the linearization at 5.1, and I'll just justify it here since 5.1 is close to 5. Since x equals 5.1 is close to x equals 5. You don't have to justify it, right? I just want to kind of point you in the right direction, because we wouldn't use this linear approximation to evaluate something like f of 6, right? That would be too far away from 5. So what we have is, well, that's going to be 5 times 5.1 minus 9. And again, like I said, our kind of brain math would probably be a lot better if we didn't have calculators. So 5 times 5.1 is no match. If you use your calculator, that's all right. But we get 25.5 minus 9, which puts me at roughly 16.5. So that's my approximation of f of 5.1, which is actually kind of elaborate, right? The f of 5.1 would be 4 times the square root of 5.1 squared minus 9. Right? Well, that's tricky. Right? Way trickier to do than what we had to do down here, right, with the linear approximation. And so that's where it all came from. Let's have a look at our actual f of 5.1 is 4 times the root of 5.1 squared minus 9, which if we do this on our calculator, right, we get 5.1 squared minus 9, square root that times 4. I get roughly 16.49 72725. 4972725. And this is, of course, from calculator. Nice. So again, we've got this overestimate. But pretty darn close. I mean, depending on what type of accuracy you need, right? Maybe if you're building bridges, going for 16.5 over 16.4972725 is not a good idea. But if we're doing, you know, just run-of-the-mill math, I'm happy with that. Right? So pretty good. Any questions about that one? Oh, okay. So like I said, these two examples that we've just done, that's what you need to know from this section. And so there's a lot of other things. There's a kind of a cool physics application where we look at the error and that kind of fun stuff. We're not going to do that just because we don't need it. And like I said, I want to spend our time doing review instead. So, but we are going to talk about differentials, not because we need it for this course, but because you'll need it for Calc 2. It'll be assumed that you've kind of seen differentials, and I'm just doing my part here. So we won't use differentials for this course, but it'll be in Calc 2. They just kind of plunk you in there and assume that you know what we're talking about when we say differentials. So, and it's really not that crazy. You could probably just not listen for a little bit now and still be fine in Calc 2. But let's talk about differentials. If we recall Leibniz notation, Leibniz, there, L-I-E-B-N-I-Z notation was dy dx. I know we said we didn't like these, and that's okay. We're not, you don't have to use them, right? But sometimes it's a little bit cleaner. But also here we're going to use them in our differentials, right? So in Calc 2 you'll use them, but we actually end up splitting them up. Okay? And so, but just to develop that, this is the derivative, right? The derivative of y with respect to x, but the derivative is the slope of the tangent line, right? So here I'm just kind of bumping you through the thought process, right? So the derivative is the slope of the tangent line, which means we could probably just write it as some rise over run, right? Which we could just say, well, that's the change in y over the change in x, right? So later, in Calc 2, 3, 4, right, we start to talk about these d's, and just kind of as deltas instead, right? There's a kind of a link there. And so this is how you get there, right? There's more to it. But that's how you get those. So when you see that dy dx, you can think about it as a change in y over the change in x, right? Deltas. Okay, so what we've got, do I want to do this huge? I guess. Why not? So what I've got, if I draw a graph here, let's say I've got some curve that might look like this, y equals f of x. And then at some point here, A. And we can draw the tangent line at A. Let's see if I can. Hey, not bad. There. So now I've got that tangent line at A, which has a slope, so not the equation of the line, but the slope is dy dx. So if I go, let's do another color here, probably just for fun. If I go out to A plus delta x, so I move out some delta x amount, then here, if I trace this all the way up to my tangent line, this distance here, let me use a different color here. My delta x is my dx. The difference though is that my change in y is not the same as my dy. So here, this distance here is my dy, right? Because that's the slope of the tangent line. But my change in y is actually only this portion here. From the curve, right? And so if we're close enough to A, right? So as long as we make these increments of delta x small enough, same thing as we were doing with those linear approximations, right? Then we get close enough and the dy and the delta y are essentially the same, right? And so what we'll say over here is that, well, maybe I'll use, what color? I'll use that dy is, I guess I'll do dy over dx is approximately equal to delta y over delta x. No issues with the dy dx, or delta x. Dx, delta x, let's translate. Right? But it's in the dy versus the delta y, there's some discrepancies. Regardless of how close we are to that point, there's going to be small errors. But overall, dy dx is roughly equal to delta y delta over delta x when x is, or sorry, when delta x is small. Nice. So what we can do, right, just to summarize what we just said, so to find delta y from x equals a to x equals a plus delta x, we treat dx and dy as being approximately delta x and delta y for small increments. So as being approximately delta x and delta y for small increments. going back to the linear approximations, right? It's only really works around A, right? So for small increments of delta x. So what we can do is, what we do is we call dx and dy differentials. So dx and dy are called differentials of x and y. Just underline differentials there. So now, if we start thinking about, oh, do you remember that? If we start thinking about dx and dy as just being the change in x over the change in, or the change in y over the change in x rather, then it starts seeming reasonable that we could separate these things, right? They've been hanging together this whole time, and they've just been one chunk of things, right? Dy, dx. But if we start with, the y equals f of x, we can write, oops. We can write dy dx equals f prime of x. So now, then what we have is that dy can be rewritten as f prime of x dx. So what we've got here is just a small change in y. F prime of x is the derivative. And then, of course, dx is a small change in x. Small change in x. But dy is roughly delta y. And on that sort of cryptic note, we'll leave it for Calc 2. Right? So we're not going to do any problems or anything. The textbook goes through and shows you examples of how to use this, but we're going to parking lot it until Calc 2. So just had to introduce it. Any questions about that? No, we'll only use the linear approximations from this section on tests in this course. Okay. So, what's on test 3, you ask? If there are no questions about 310. All right. Let me find a fresh page here. So, test number 3 is going to be on, is it on sections 3.5? And then we didn't do 3.6? Is that true? No, I don't have it written down. Yeah, but we, 3.6, I'm just trying to remember what 3.6 was. Oh, was that logarithmic differentiation? 3.5, 3.6, 3.7, 3.9, and 3.10, right? Just not 3.8, I guess. Even though you, there's no real stuff going on, it's just developing kind of population curves and stuff like that in 3.8. So you definitely could do it, but you don't have to. All right. So first question on the test is just implicit differentiation, right? So implicit differentiation I give you a function, you have to use implicit differentiation to find the derivative. That's it. Question 2 is going to be, you have to find the equation of a tangent line. Whoa, sounds familiar, right? With implicit differentiation. Find the equation of a tangent line with implicit differentiation. Question 3 is going to be using logarithmic differentiation, and it'll even say use logarithmic differentiation to solve this thing. Logarithmic differentiation. And then, although it's nice to have them kind of in order, in the order that they appeared, for spacing reasons, the linear approximation one comes after that. I think you can handle it, right? So then there's a linear approximation, which we just did, a linear approximation. Fifth question is one of those velocity questions, just kind of setting you up because you'll have to see it on the final again. So just want to make sure that you're prepared for that, but really not that bad, right? I'll call it a velocity question. So we give you the equation for the displacement of some particle or some car or some whatever, right? So you get the equation for the displacement, and it'll ask you things like when is it at rest? What's the velocity at time equals 2 minutes? Things like that, right? So remember that the velocity is the first derivative. You're not going to need it, but acceleration would be your second derivative, right? And so we have to take the derivative of this thing to evaluate it. So there's going to be a velocity question. Question 6, you have to find the derivative of an inverse trig function. So just don't evaluate it or anything. Just remember you've got these differentiation rules to memorize, right? I'd focus on the left-hand side. Those are the more important ones, right? We already derived arcsine and arctan, so sine inverse and tan inverse we derived in class. And so the only new one that I would make sure that you know is cos inverse, right? The right-hand side, they're a little bit extreme. I wouldn't do that, right? So it's going to be from the left-hand side, kind of our go-to. Sine inverse, cos inverse, tan inverse. And so find the derivative. Find the derivative of an inverse trig functions or trigonometric function. And then finally, question 7 is the related rates question. And I will say that it's going to be a similar triangles one. Similar triangles, which usually ends up being, so Steve and I were brainstorming yesterday what we could make it, because I was like, oh, I hate those shadow problems. The shadows, I guess I don't understand how shadows behave. And so I personally do not like shadow questions because I have a hard time figuring out how the shadow would behave. I know that's really stupid, but I don't know. So I was like, Steve, can we make a similar triangles question without using shadows? So we were trying to figure out what we could do. Turns out not really. We end up always using shadows for similar triangles. And so, but we really wanted to use a similar triangles one because that's what you'll have on the final. And so that's why we wanted to prepare you. I guess the other one is a cone, right? If you're filling a cone or a cone has a leak, but we can't use that on the test. So we have to use a shadow one. So we've got similar triangles, which is going to be kind of, there's going to be a light source and shadows. So what I did was, of course, I Googled related rates with similar triangles, could not find a single one that was in a shadow one or a cone one or something like that. So I guess we have to use the shadow one. And I actually posted on Moodle, let's see here, if it'll take me there. It's just a link to Khan Academy, but I thought it was a really, well, of course, Salcon can do no wrong. And so there's the related rates shadow example. What a guy, right? So he explains it way better than I ever could. And I don't know how he is able to explain things so well. He must rehearse it like a billion times. But anyways, so here you've got the link to the one, the only Salcon doing a related rates question with a shadow. So he's doing the shadow of a diving bird. He's got a very elaborate setup, but anyways. So have a look at that, kind of watch that for more help, right? And then you can always, there's tons and tons of shadow questions online. If you just Google, right? And I've got one ready to go for us to go through, but definitely you'll want to have a look at more, right? And so if you just Google related rates, similar triangles, all those shadow ones will come up, and there's tons with solutions and just kind of walking you through it and stuff like that, right? Once you've done enough of them, right, then you'll start to kind of see the pattern. And I guess I get it now, but I don't know. I don't blame you if you have a hard time with the shadows, but I am warning you that there will be a shadow question on the test. Okay, so I don't know. I'm not ashamed to say I don't like the shadow questions. It's just how it is. I don't have to like it all. So that's your test, though. I I know it looks long, and you will want to kind of keep your pace up. You don't want to get hung up on one question for too long, right? But especially these first, I want to say, probably 4 questions should be pretty quick, right? You're just kind of finding derivatives and using them, right? And so, all right. So, what do we want to do? What would you most like to see? Implicit diff. What? Sure. Let's do it. And the shadow one. Okay, fine. The only one that I don't have one that's prepared right now is for the velocity one, but I also feel like that's probably okay because I can post some extra practice problems with solutions just so that you have them. Oh, well, we ended up going through all the ones that aren't in the textbook. So the rest of these are just from the textbook. So you can, yeah, 1 through 4. And I think we even did, can't remember if we did a couple of these. We did 1. So 2, 3, and 4 are the only ones. Oh, maybe 5, but we did that one. Yeah. They're just in the textbook. Yeah, so I just stole those. So you've got those solutions, so that's why I didn't. Yeah. Good. Whew. All right, so let's do some practice problems. Implicit differentiation. Should we do just we can do both. I think, hopefully, I think we got time. So if we've got something like x sine y, oops, plus y sine x equals 1, find dy dx. So now I've got x's and y's, they're all baked in. It even says, find dy dx by implicit differentiation. And then it just gives you the thing. So you'll know you have to use implicit differentiation. But the reason is because the x's and y's are intertwined and there's no way of separating them. Right? And so if we have to find d dx, actually, just for, usually we drop the y on the outside because now I'm saying, okay, I want to find the derivative of all of this stuff with respect to x. So I'm going to ditch that x or that y for a bit and put x sine y plus y sine x equals 1, all in brackets. Just making some notes of the setup here. I've got a product and another product. So I'm going to have to use the product rule on each of these components, which means I'm going to have 4 terms, right? So what I get is, and so what we'll just make a note of here is that the product rule shouldn't use equals. I guess it's just the statement. The product rule is just going to be, and it depends on if you want to match, where did I have it? How's it set up? GF prime. So it depends on if you want to match the quotient rule or if you want to just go for it. It's FG prime plus gf prime on your kind of thing to memorize, right? Or if you wanted to, right, because we're adding, you can rewrite them in the order that they appear in the quotient rule. But remember, in the quotient rule, you're subtracting up top, but you've got gf prime plus fg prime, right? So whichever order you do is fine because we're adding, right? So, and the gf prime plus fg prime is to match the quotient rule, which says that we want gf prime minus fg prime over g squared. Oops. Now we're not using the quotient rule, but I just wanted to kind of highlight that. So as long as we're consistent, right, taking the derivative of one, multiplying it by just the other one held steady, and then adding the other one held steady times the derivative of the other one, so many other ones. It does make sense. So we've got x sine y. So if I take the derivative of x and multiply by sine y, I'm left with sine y plus, and then holding x steady, the derivative of sine y is going to be cos y. Okay. But y is a function of x, right? So whenever you're taking the derivative of something with y in it, right, you can just take the derivative the normal way, but you have to multiply it by dy dx. Okay. The derivative of y with respect to x, because you don't know what's going on inside that y, right? So you have to use the chain rule. Y isn't necessarily y, it could be something like x squared plus 1 or something weird like that. So then you have to multiply it by dy dx, which in that case would be 2x, right? And so that's why we've got that dy dx. Okay, so that's that first part. And maybe I'll put big square brackets around this just to indicate that that's the first product rule done. And now I'm adding the second product rule. You don't need those big square brackets, but I think it's nice. So if I take the derivative of the first thing, so the y, I get just dy dx, or y prime if you prefer, right? Wherever you see a dy dx, you could write y prime if you wanted to. If I take the derivative of y, that's just 1, but then I've got dy dx, right? The derivative of y with respect to x. Or if you prefer, you can just replace that with y prime. So dy dx times just sine x held steady plus, and then now y is held steady times the cos of x equals 1, the derivative of 1 with respect to x is 0. So I've got these brackets, they're not doing anything. I can just kind of rearrange things here, because what I'm doing is I want to solve for dy dx, right? We want to find dy dx. So now I can rearrange things, and I get, I'll have to move my equal sign over, so I'll collect my dy dx's on the left-hand side and everything else on the right-hand side, so just kind of moving things over. X cos y dy dx plus dy dx sine x equals negative y cos x minus sine y I can pull out that common dy dx. So I get dy dx times x cos y plus sine x equals, and I'll pull out that negative y cos x plus sine y. Not that it matters, but it just looks nicer, maybe. To solve for dy dx, all I have to do is divide both sides by x cos y plus sine x, And so here I'm left with dy dx is negative y cos x plus sine y divided by x cos y plus sine x. Ta-da! So the only trick with implicit differentiation is that if you take the derivative of a y, you just do it normally, but then you always just multiply it by dy dx or y prime if you prefer. Right? And so that's the only thing with implicit differentiation. Yeah. So we wanted to do a logarithmic differentiation, and just looking at the time here. How about we do another one of these implicit differentiation ones, because I think we'll still have time to do logarithmic and the shadow one. I guess this is practice question 1. Question 2. Give an equation of the tangent line to the folium of Descartes x to the 3 plus y to the 3 equals 6xy at the point 3, 3. So our x's and y's are all baked into the same. There's no way that I could kind of tease out a y here and get y on its own, or at least not easily. And so I'll just use implicit differentiation for this guy. And here it doesn't say use implicit differentiation, but you'll have to anyways. So if we have x to the 3 plus y to the 3, if I want to find the derivative with respect to x of this whole thing, x to the 3 plus y to the 3 equals 6xy, I need to remind myself that, okay, here I've got the product rule, x times y. So I'm going to have to remember that. But the rest of it, oh no, Trudeau's self-isolating. We all need a break. Poor Tom Hanks. Rita Wilson. So then we get 3x squared. That's fine because there's an x in there. And so we can just take the derivative. But then when we take the derivative of y to the 3, we still get 3y squared, but we have to multiply it by dy dx. Right? Because we've got that y in there. So, and we don't know what's happening in the y. And just as a rule, whenever you take the derivative of y, you have to just do it, but also multiply by dy dx. So it's got that added component. And then I've got the product of 6xy. And so if I do the derivative of x, I get 6y plus 6x. And then the derivative of y is just going to be 1, right? But then I have to multiply it by dy dx. So our goal here, right, we're finding the equation of the tangent line. So I know I have to find the derivative because that's how I'm going to find the slope at 3, 3. And then I have the point and the slope, so I can use the point slope form of the line to find the equation of the tangent line. So here I'm just solving for dy dx and moving my dy dx's over to one side. I get, let's see here, I get 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. Hopefully I didn't. That looks good. So if I pull out the common dy dx here, I get 3y squared minus 6x equals 6y minus 3x squared. Solving for dy dx, I get 6y minus 3x squared over 3y squared minus 6x. We want this thing at the point 3, 3, right? So when x equals 3, y equals 3. And so at 3, 3, the slope of the tangent line dy dx is 6 times 3 minus 3 times 3 squared over 3 times 3 squared minus 6 times 3. I'm looking at -9 over 9. 6 times 3. And then 3 squared times 3. -1. So now I've got a point, I've got a slope, I've got y minus y naught equals m times x minus x naught, because I find it helpful to write out the general formula. So I've got y minus 3 is -1 times x minus 3. I can simplify this a little bit. So I get y is -x plus 3 plus 3. So I get y equals -x plus 6 is the equation of the tangent line. And then we're done. Logarithmic differentiation. So problem 3 that we'll look at says use logarithmic differentiation to find the derivative of the given function y equals 2x plus 2 to the power of x squared minus 1. Remember from that handout on the new section, right, when to use logarithmic differentiation is if you've got x's in the base but also in the power, which we have here. So we would probably, even if it didn't say use logarithmic differentiation, to bring that x from the power down, I would probably end up using logarithmic differentiation anyways. Because remember, the goal of logarithmic differentiation is to just simplify finding the derivative, right? And so if we take the logs, and I always use the natural log, I'll always use the natural log just because it has that nice derivative of 1 over x, right? And so that's easy to deal with. And so we're going to use the natural logs. So we take the natural log of both sides, of course. Can't do to one what not the other. So then I have the natural log of y, and I just write my ln's as a kind of a squiggly mess, but ln y, and wrap this whole thing up in an ln, 2x plus 2 to the power of x squared minus 1. By the log laws, I can bring that x squared minus 1 down in front, right? So then I get x squared minus 1 times the log of 2x plus 2 is the log of y. Now I can take the derivative. Yeah. So now take the derivative. The derivative. Yeah. Notice though, right, that we've got a little bit of complications, right? We've got a product, x squared minus 1 times the log of 2x plus 2, but we've also got the chain rule on the log of 2x plus 2, right? And so here I've got a chain, but out here I've got a product rule. So we'll have to keep those separate, but that's going to be a lot easier to deal with than what we were looking down at before here. So on the left-hand side, the log of y, we can just take the log of y, and that's just 1 over y. But when we're taking the derivative of the logs, then we have to, of y, we have to times it by dy dx, or y prime if you prefer. Which is going to be, okay, so we've got the derivative of one of the things, right, times the one held steady. So it just depends on how you like to order your product rule. And so I'll take the derivative of x squared minus 1 and leave the log 2x plus 2 for a little bit, right? But if you want to make it match the quotient rule, that's fine too. So here we've got the derivative of x squared minus 1, I'm just looking at 2x here, don't even need brackets. So 2x times the log of 2x plus 2 plus, and now I'm holding x squared minus 1 steady, and I'm taking the derivative of the log of 2x plus 2, which is going to be 1 over 2x plus 2. But I have to multiply it by the derivative of the inside. The derivative of 2x plus 2 with respect to x is just 2, so times 2. We can simplify this a little bit, and remembering that we want to solve for dy dx, right? And so we want to solve for this guy here. So we've got, I'll keep the 1 over y for another step here, dy dx, which is going to be, okay, here we go. What can we do? Not a whole lot, actually. I can bring that 2 on top. Yeah, there's not a lot that I can do, so maybe it's okay. Let's do that. We can. Why not? So I get 2x times the log of 2x plus 2 plus x squared minus 1, and then 2 over 2 times x plus 1. It's not even something that I would expect you to do. And that's kind of above and beyond for the cancellation.
So we can can x squared minus 1 squared, something like that?
Yeah, probably. I don't want you to go that far. I don't even want you to go that far necessarily, right? You could just squish the 2 on there and kind of move on. So here, what we've got is, if we're solving for dy dx, I can multiply both sides by y, right, to move that y over. So y is times 2x times the log of 2x plus 2 plus x squared minus 1 over x plus 1. And yeah, it looks like we could cancel that, but it's okay. Doesn't matter. Remembering that y, right, we know what y is, right? So we just plug that in for y, and 2x plus 2 to the x squared minus 1. So 2x plus 2 to the x squared minus 1 times 2x log of 2x plus 2 plus x squared minus 1 over x plus 1. And that's it. Then we're done. So unless it's obvious simplification, then go ahead and do it. But if you're finding that you have to work to simplify something, it's not something that I'm expecting, right? Just kind of find the derivative. That's the key here, right? Being able to find these derivatives. Okay. Shadow time. Shadow time. All right. It's another flashlight. The question was 3, 4. A flashlight is placed on the ground at a distance of 20 feet from a wall. A 6-foot-tall person walks at a speed of 2 feet per second. Walks at a speed of 2 feet per second in a straight path from the wall towards the flashlight. From the wall towards the flashlight. When the person is 8 feet, when the person is 8 feet from the wall, how quickly is the height of his shadow increasing on the wall? How quickly is the height of the shadow increasing on the wall? Okay. So first thing, for 1 mark, let's sketch this thing out, right? Let's just figure out what this looks like. So if I say that I have a wall over here, and I'm placing a flashlight down here, pew, pew, pew. Then I've got a flashlight here. And what else were we told? Flashlight is placed on the ground at a distance of 20 feet. So this distance here is 20 feet. Okay. A 6-foot tall person walks at a speed of 2 feet per second in a straight path from the wall towards the flashlight. Okay. So here he is, he starts at the wall, and at some point here, he's kind of, he's walking like this. Ah, so he's under arrest. Hands up. Right. Oh, and I guess he should be on the ground there. Right? All right. So I guess just as a fact, how shadows work is as a triangle. So the triangle is going to go, so if we're making, oops, helps if I'm drawing. If we're drawing a shadow, this shadow, oh, I'm gonna have to make them taller or just start over my line. I'll draw a solid line so it's easier to erase if I screw up again. I guess this is just how shadows work. And I guess that's what I had to kind of come to grips with. Just triangles. So here, right, if he starts by the wall, then, I mean, the whole light is on him, but if he moves away, right, then he's got his tallest possible, shortest possible shadow, right? How does it work? How do shadows work? Anyways, this is what we're gonna do. This is what we have to do. Okay? So what we're saying is that, okay, if we let, because we need variables, right? We need to find the height of the shadow is increasing. Oh, I see why it's increasing. Because if he moves out this way, yeah, because then his shadow would be bigger. I get it now. I'll probably lose it, but slowly but surely I'll understand shadows. Maybe. All right. Well, that's not really helping my, but it helps my understanding. So, okay, cool. Great. So now, what we need is we need to relate the rates that he's moving, because that's the rate that we're given, right? And so we need to relate the rate that he's moving out from the wall at to the height of the shadow, right? And so what I'm going to do is I'm going to assign some variables here, because I know this rate that he's moving at is 2 feet per second. Right? So if I assign this to some variable x, right, usually if I'm moving in the x plane, I call it x. If I'm moving in the y plane, I call it y. And so, and I call this y. Then what we know is that dx dy, or sorry, dy dx not dx, it's with respect to time. 2 feet per second, of course. Dy dt is going to be the rate of change of the shadow. Oops. And then dx dt, so related rates will always be in terms of time, right? Because he's moving in time. Dx dt is the rate of change of the man, which is 2 feet per second. So we know dx dt, and we want to find dy dt, right? How quickly is the height of the shadow increasing on the wall when x equals 8?
Is it the displacement or the speed we are talking about? The rate of change of the man.
So
how quickly it is displacing its position?
Yeah, so it would be the velocity, right, with respect to time. Yeah. So we know dx dt is 2 feet per second, and we want to find dy dt, which means that I need to find some sort of function that relates x to y, and how I'm going to do that is through similar triangles, right? I've got this this little triangle here. How can I draw it? Oh, I forgot to put that he was 6 feet tall. So let's do it in green. What I've got is I've got this triangle here. And then the larger triangle. So using similar triangles, I say that 6 is to y as 20 minus x is to 20, right? Because here, this distance here is 20 minus x. So it doesn't matter how you slice it and dice it, right? As long as you're relating the similar triangles, right? The sides of the similar triangles. And so if we start with the 20 minus x is to 20. As 6 is to y. As 6 is to y. So that's how I set up my similar triangles. I just talk myself through it, right? So 20 minus x is to 20 as 6 is to y in the larger triangle. Okay. So now I can cross multiply and I can sort this out a little bit. And so I get y times 20 minus x is 6 times 20. 6 times 20, oops, I almost did 120. Turns out I know it after all, is 120. So I get y, or let's do 20y minus xy. Actually, I think it's going to be easier if I just keep the y on the outside. It doesn't actually matter, but it will be, because I know I'm going to have to take the derivative of this thing. So it's actually easier if I just keep the y on the outside. So let's just y times 20 minus x. And you'll start to see that stuff too, right? Do you want to do two product rules, or do you just want to do one product rule? I don't know. Doesn't matter. Or I guess 1.5 product rules. Anyways, it's easier this way. So if we use similar triangles, then relationship, we set it up that way. Oh my goodness, I'm way out of time, aren't I? The related rates. How about I'll finish this and post it on Moodle, because I know you guys have class and stuff. So I'll finish this. As always, I'll post these notes on Moodle. They'll just be at the end, of course. Any questions? Okay. All right. Maybe I'll even pause the recording and finish it in my office. How about that? Okay. It's been a few hours here, so let's see. All right. Now I remember. Okay. So now we have to find the related rates, which means I need to find the derivative of this thing. And so what I'm going to have is I'm going to have a product rule here. I need to break that thing up. And so I've got, if I take the derivative of y, then I get dy dt times 20 minus x. And then plus leaving the y on its own times the derivative of 20 minus x makes just -1, and then dx dt, right? Because I took the derivative of x, but because I'm not taking with respect to x, I'm taking it with respect to t, I need to add on the dx dt regardless. So it's not like implicit differentiation where we had to just tack on the dy dx when we derive with respect to y with respect to x, but now we're taking the derivative of y and x with respect to t, so they're basically both implicit, but then taking the derivative of 120 with respect to t, either way, it's going to be 0. So now, remember, we said, okay, we know dx dt is 2 feet per second, right? And so let's have a look here. If I know dx dt is, let's use that other color again. So this is going to be 2 feet per second. Going back to the question, right? We said, okay, well, when the person is 8 feet from the wall, so x is going to be 8, right? Then we can figure out what y is. Right? And so here, let's see here. So x is going to be 8. Okay. And if we're figuring out what h is, so sorry, not h, using old notes here. If we're figuring out what y is, well, we've got this triangle, right? I'm told that this is 20, and this is, oh, you know what? Let's make it even easier. Never mind. I guess I should have reviewed this stuff anyways. Before jumping into it, here we go. I'm going to use this equation instead. Right? That's way easier to solve for y. So I've got y times 20 minus x is 120. So, right, where'd it go? It's closer than you think. It's even on the same page. So y times 20 minus x equals 120. So then if x is 8, we get y times 20 minus 8 is 120. So we get 120 divided by, well, I guess 12. So I get y must be 10. Nice. So the only one that I don't know is dy dt, which is the one I want to solve for. I want to solve for dy dt. Let's plug in those numbers. So we get dy dt is, times 20 minus 8 plus 10 times negative 1 times 2. We just want to make sure that we have the right, if it's positive or negative, equals 0. So let's just convince ourselves, right? And so a 6-foot tall person walks at a speed of 2 feet per second in a straight path from the wall towards the flashlight, right? And so here he's walking this way, right? And so this is going to be positive, not because it's in the positive direction, well it is, but also because x is increasing, right, as we move out this way. So dx dt is positive, and so here, let's do this. We'll just put that on there. It should be positive, which it is, so that's good. All right, so now we can simplify this a little bit, and we can say, okay, well, we've got dy dt times 12, and then we've got 10 times 2 and negative, so minus 20 equals 0. So I get 20 divided by 12. Okay, so I get dy dt is 20 divided by 12, positive. So let me just try that again. 20 divided by 12. Which is roughly 1.666 repeating feet per second. Nice. Okay, so this here, just as a note, this is the exact answer. Right. You could simplify it, right? There's common factors in there, but 20 over 12 is the exact answer, and this is your approximate answer. Cool. All right. See you later.